Electricity must be generated at the time it's used, but demand for electricity fluctuates throughout the day and throughout the year. So it's a challenge for utilities to match their generation of electricity with the demand for electricity in an efficient, cost-effective manner. Traditional power plants have long startup and shutdown cycles. So for these plants to meet peak demand, they must generate more electricity than is needed during off-peak hours. This is expensive, inefficient, and produces unneeded greenhouse gases. Currently, smaller gas-powered units are turned on to meet peak demand. These peaker units are expensive to operate, so the electricity generated is expensive for consumers. If generation doesn't match demand, the result is a blackout the instant that mismatch exceeds a critical level. Californians want their electricity produced from ecologically sustainable, renewable resources like solar and wind, and they want that electricity at the lowest possible price. Production of renewable energy varies with the amount of sunlight or the strength of wind, and it may not be generated when consumers need it.
Energy storage is a key component to having a stable electricity grid, being able to integrate large amounts of renewable energy resources without a lot of interruption. This can be addressed in a number of different ways, including using geographic diversity, where the wind's blowing in one place and it's not blowing in another. They can complement each other. Or you can deal with those interruptions by using electricity storage.
There are two primary forms of utility-scale energy storage: low-cost bulk storage, which provides long-duration power, and high-cost short-duration storage. Flywheels and batteries are short-term storage, used close to the consumer, and typically provide backup power, which lasts from minutes to from 2 to 4 hours. It's impractical to build large-scale battery or flywheel storage. The alternative is bulk storage, which can provide large-scale energy solutions by taking advantage of unique geologic features. There are two primary forms of bulk storage: pumped hydro and compressed air energy storage. These energy storage systems can typically provide electricity when needed for more than 24 hours. Pumped hydro facilities are very expensive to build and require large reservoirs of water, which are in short supply here in California. Most pumped hydro facilities were built in the 1960s, and few new ones are being considered today. The alternative is compressed air energy storage, where compressed air is pumped into large underground caverns to be used later to generate electricity. Compressed air energy storage, or CAES, provides low-cost, scalable storage far from urban areas with a very small footprint.
Based on research and development activities and even some of the demonstration plants that EPRI has been involved with over the years, it seems currently that the most attractive energy storage technology for California is compressed air energy storage. Number one, it's the least expensive. Number two, it has the best round-trip efficiencies. Number three is the lowest maintenance cost. So it's commercially available, it's reliable, it looks to be the most cost-effective.
The first U.S. CAES plant began operation in 1991 at the Power South facility in McIntosh, Alabama, utilizing equipment built in America by industry leader Dresser Rand. Over its 23 years of operation, the plant has been able to demonstrate the ability to deliver low-cost, reliable, large-scale storage with fast startup capabilities, going from idle to full power in 10 to 15 minutes. So how does CAES work? In the compression mode, low-cost, off-peak electricity that might have been wasted is brought in from the grid to power a motor and the compressors that pressurize the cavern. Air is compressed and pumped into an underground salt cavern. In the power generation mode, the compressed air is released, then combined with heat to power turbines, which drive a generator producing electricity. What makes CAES storage truly unique among energy storage solutions is, first, the ability to increase the amount of storage in 150 megawatt increments by adding additional CAES modules, and second, the ability to store energy and provide power simultaneously.
The smart CAES system with two trains allows you to actually use both trains, both the compressor train and the power generation train, at the same time to provide different services to the grid. For example, you may be taking advantage of low electricity prices to charge the cavern at the same time that you're running the turbines at low power or moderate power to provide frequency regulation or reserve capacity.
Dresser-Rand's smart CAES technology has put unparalleled flexibility in the hands of grid operators and dispatchers.
The compressors are very robust. They're derived from designs that are made for critical hydrocarbon service in refineries, offshore platforms, and chemical processes. So using air is a pretty benign service for these machines, and they go very long periods between overhauls. The turbines, by comparison to gas turbines, are very easy to maintain. They operate at relatively modest firing temperature, so we can go 4 to 7 years between major overhauls on the expanders, and the hot flow path parts are less complex, less expensive, and cost a lot less to repair or refurbish than for conventional gas turbines.
So why hasn't more CAES storage been built in the United States? The simple answer is that CAES requires a unique set of geological conditions not found in most parts of the country. The most notable CAES development being considered is located near Delta, Utah, where the potential storage exceeds 1,200 megawatts. For California, CAES storage is an important way to meet our renewable energy targets and provide low-cost, clean energy storage on a large scale without impacting urban areas or the environment. CAES is proven technology and right for California's energy future.